Understand the extreme value theorem. So next up, we need to talk about the extreme value theorem. And this is an important theorem for us, especially moving forward when we start talking about applications of derivatives. All right, so before we dive into what the extreme value theorem is, let's just quick review what we know about absolute and global extrema. We know that graphs can have both an absolute max and an absolute min. It can have an absolute max or an absolute min, or it can have neither. So as we demonstrated on the 7 graphs we previously looked at, we saw graphs that had both an absolute max and an absolute min. We saw graphs that had neither an absolute max or an absolute min, and we saw graphs that had one or the other. All right. So let's talk about the extreme value theorem and what the extreme value theorem says about absolute or global extrema. Well, the extreme value theorem says that a function that is continuous on a closed interval AB is guaranteed to have an absolute maximum value and an absolute minimum value on that interval. So this is huge, because the extreme value theorem is telling us that if we have a continuous function on a closed interval, we have to have both an absolute max and an absolute min, which is good news. So whenever we have a function on a closed interval, boom, has to have a max, boom, has to have a min. So let's take a look at some graphs and how we would go about this. All right, so we can see here is our graph of something that looks kind of like a cubic function, a little bit off though. But we can see here that this particular function has no absolute max or absolute min, because the end behavior goes to negative infinity and positive infinity. However, if we do cut this off and make it so that it's on a closed interval, so we kind of trim this a little bit, and we just look at the function over this closed interval from a to b, we can see that we are guaranteed then to have an absolute max, and we are guaranteed to have an absolute min. So again, by restricting the domain of the function and forcing it to be on a closed interval, we go from having a graph which has neither an absolute max or an absolute min to a graph having both of those things. We can do a similar thing with a parabola. However, with a parabola, we know that it already has an absolute minimum value at the vertex. Boom, good. However, we don't have an absolute max because the end behavior goes towards positive infinity on both sides. However, if we do come in here and we do kind of restrict the domain, and we kind of truncate our function from a to b, we can now see that this particular function has 2 absolute maximum values because they both share the same height. And we take a look at one more. This particular function, it has local extrema, but it doesn't have absolute extrema because our endpoints, or excuse me, our end behavior are going towards positive or negative infinity. But just like we did before, we can come in and we can truncate the function. We can restrict the domain to being from a to b. And when we do that, we create an absolute max up here, and we create an absolute min value down there. Something to keep in mind is that based on what we are looking at here, absolute max and mins can be turning points. But when we restrict the function to have a closed interval, absolute extrema can also be endpoints. So, when we are trying to find absolute extrema, we need to check the endpoints, and we need to check the turning points. So let's take a look at how we can do that. So our first example is if f of x, is f of x equals 3x over the square root of 5 minus x guaranteed to have an absolute maximum. Oh, wow, let me retake that. One more time. Is f of x equal to 3x over the square root of 5x guaranteed to have an absolute minimum and maximum on the interval 0 to 4. So here we're not actually trying to determine what the absolute max and the absolute minimum value are. We're just trying to see if it's guaranteed to have an absolute max and an absolute min. So, in order for it to have an absolute max and absolute min, or in order for us to apply the extreme value theorem, two things have to happen. There are two conditions for the extreme value theorem. First condition is f of x continuous on our interval 0 to 4. And the second condition is f of x on a closed interval. Alright, so if we look at is f of x continuous on 0 to 4, well, our f of x value is a fraction. We know a fraction is not continuous when the denominator equals 0. So to find any x values for discontinuities, we need to set the denominator 5 minus x equal to 0. And then we can just start to solve this. We'll square both sides to get rid of the square root. 5 minus x equals 0, so therefore x equals 5. And this is where we have a discontinuity. So our f of x function is not continuous everywhere, but that's not what the extreme value theorem asks. Extreme value theorem needs it to be continuous on a specific interval. And since 5 is not in the interval 0 to 4, boom, this condition is met. Then on to the second condition. Is f of x on a closed interval? And as we can see up here in the problem, it is on the open interval 0 to 4. So that condition is not true. So therefore, the extreme value theorem does not apply. All right, let's take a look at one more of these guys. So next up, is f of x equal to 1 over the natural log of 3x guaranteed to have an absolute maximum and minimum value on the closed interval 1/4 to 2? So just like before, we need to check our two conditions. First condition is f of x continuous on our interval 1/4 to 2, and then is f of x on a closed interval. And while the second condition is the easiest one, we can see that our function is on the closed interval from 1/4 to 2, so that condition is met. All right, let's go back up to the first one, asking if f of x is continuous on that interval. So we can see our function here is a fraction. We know fractions are not continuous when the denominator equals 0, so we'll just take natural log of 3x, set it equal to 0. All right, so then we want to get the 3x by itself, so we need to get rid of the natural log. And to do that, we'll take the e of both sides, because e's and natural logs are inverse functions, giving us 3x equals e to the 0th power. Well, e to the 0th power is 1, so we get 3x equals 1, so therefore x equals 1/3. And this is our discontinuity. All right, so now we just need to check, is 1/3 in our interval 1/4 to 2? And unfortunately, it is. 1/3 is larger than 1/4, so therefore 1/3 is in between 1/4 and 2, which means it's not continuous. So unfortunately, the extreme value theorem does not apply again. All right, folks, that is understanding the extreme value theorem.